Hello, welcome to graphing motion number 2. What I'm going to do is show you how to read a distance versus time graph and to graph the velocity versus the corresponding velocity versus time graph. So as you can see, I have a object that is moving at different intervals and different rates and whatnot. And what I'm going to do, like I said, is break this down onto this graph right here, velocity and displacement. So what I'm going to do first is to kind of separate out some of these motions, and this way when I plot it, it's the same. So in other words, actually, I think what I can do, I'm going to use something fancy, right? So I'm going to break apart, each section. So at 2 seconds, at 2 seconds, or close to 2 seconds, well, I guess if I'm going to do it, I might as well do it right. There we go. I'm going to plot the 2 seconds, This will be the first section, right? Notice that we have another motion going on right here at like 2.5 seconds, so same thing. 2.5 and 3, this is a very small area right there. Then we have it at 4 seconds. Let's do it at 4. There we go. So if you see what I'm doing is I break down the straight line, then I have an angled line, now it's a straight line, and I have this is at 4. And this is something I suggest you do too. Close enough. And just the general idea. So from here to here, it's its own motion. This thing's moving a lot. So this thing curves to about here. I'm going to call it at 7. Even though there's a little slight curve, that's okay. I'm just going to estimate more or less. So I'm going to actually do this too. So I have one at 5. So from 4 to 5 I got to look at. And then 7, 5 to 7, 7 to 10. Okay, so these are all my regions, if you will. And just to make it look nice, I can do this. Just cut off the top right. There you go. Just to make it look nice. Cut off the bottom. You don't have to do this. Alright, so now that I did that, I'm going to look at each part. So more or less this is like section 1, section 2, section 3, section 4, section 5. So anytime of problem solving, it's always good to break things down because that's how you're going to organize your information and see it a little more clearly. So right here, section 1, we have an object that maintains its position over 2 seconds. So when we do that, that's going to be a 0 velocity. So I'm actually going to do it in a color that we can see like blue. So 0. I'm going to make sure it's right on the 0 mark. So 0 velocity. Right on that 0 mark line. So check this out. This is going to be now moving because we change our position. We go from point 3 to point 8. So let's do section 2. And we do that in 1/2 second. So I'm going to find the slope. So remember, the slope tells me the velocity. So delta x over delta t. So my change in position, I go from point 8. Go. And I started at point 3. These are in meters, like that. And my change in time, you can see, is 1/2 second. So I'll do 0.5 seconds to get my numerical value of that. So 0.8 minus 0.3 is 0.5, just double checking. Okay. So we get 0.5 over 0.5, which makes, that should be in seconds. There we go. 1 meters per second. And it's positive because we're increasing. So, I don't think this is going to go beyond 3. So let's make a label here. Let's call this 1, 2, 3. I'm not going super technical here. Just the main idea. So at 1 meter per second, we're here during that interval. So yes, there's going to be a jump because literally we do that. We go from not moving to basically jumping into motion. So that's why this line is right here. Alright, let's take a look at this section. Notice that we maintain this position, section 3, during this time. So this also goes back down to a 0 velocity right there. So I'm making it very dark just so you can see that it's on the 0 mark. So that's section 3. Let's take a look at section 4. We go from point 8 to 1.1. So I'm finding the slope of that. 1.1 is our final. Our initial is 0.8. Some of you can do this in your head. That's totally fine. You can definitely take shortcuts when you want to. But I like to write it out. The time interval is between 5 and 4, or 1 second. Notice that I didn't write 5 or 4. I just wrote the time it took to do that. Technically, you could do 5 minus 4. That also works. So I'm taking a shortcut by doing this. So I get 0.3 over 1 second. So as you might imagine, I get 0.3 meters per second. So about a third. So let's go about right here. Let's estimate that as about a third. Okay, let's take a look at this. From here to here. This is technically an acceleration because what we have is a slight curve. Notice how we start off not moving fast and then we actually gain more speed right here. But what I'm going to do is, since it's such a tiny acceleration, so just a note on that again. Anytime you see a curve, that's an acceleration. But let's just simplify this as a straight line. So what I have here is 2 points. I'm going to do that just to make it a little easier. If the curve was more drastic, I would actually find the acceleration, but let's just keep it like this. So that again is going to be a slope. So when we find the slope, it goes from 1.1 to about, I don't know, 0.05. Again, I'm estimating. So our final position is 0.05. Our initial position is 0.0111. And this takes place over 2 seconds. I got 2 because 7 minus 5, this duration is 2 seconds. So this gives us our first negative number. Oops. 1.05 minus 1.1 gives me 0.05 divided by 2. 0.05 meters divided by 2 gives me negative 0.025 meters per second, like that. Okay? So now that we have section 5, and let's write this out. So this is, I said every 3 it looks like. So let's keep that consistent. So like right here is about 1, this one's about 2, negative 1, negative 2. So this one will go below because it's negative. And it's negative about 0.2, so about a quarter. It's actually a very, very small speed. So let's see. It's like a quarter of a quarter, so it's way over here. It's not 0, but it's pretty small. And again, I'm estimating here, so you're just getting the idea. But the more important thing is that it's negative. It's below the line in this one. And then let's look at this one, the last section 6. So same thing, I'll take a slope. So if I take the slope of this, what I get is we start off at 1 and we go to 0. So remember, by the way, I'll write this here. I am doing this the whole time. I might be taking shortcuts, but I'm doing final minus initial for each thing. Okay? And we know that the slope of this is our velocity by definition. So that's why I'm solving everything with slopes. So let's do this. So the final position is 0. The initial was 1, a little above 1. It's not 1.1, like 1.05. Let's just start from where we ended off over here. Now we do this in 1, 2, 3 seconds. So we get negative 1.05 divided by 3. Then we get negative 0.35. And this is meters per second, like that. So this one's more of a third. So this one goes more on this line. Now it's constant velocity in all these cases, and that's because of this straight line. So straight lines, so straight on a distance versus time graph equals constant. It means you're covering the same distance over the same time. And that's why these lines are all flat. They're flat because they're constant rates. Constant velocities. Except for this section, but like I said, I simplified it. So technically we would see that this actually went from moving to not moving. And if I wanted to account for the acceleration for this slight curve right here, I'm speeding up because I'm covering more distance over here than over here. It's more flat, which means I'm resting more than over here. So I'm speeding up, but also speeding up while going backwards. So what's going to happen is that technically, if I were to draw this more correctly, it would be a straight line because I would be speeding up backwards like that. So I go from I slow down and then, yeah, so there we go. That's what it looked like. But don't worry about it too much with this problem. So there you have it. That's how you can make the displacement go to velocity by taking the multiple slopes of these graphs, okay? Hope you enjoyed.